Now that we know how to take the determinant of 2 by 2 and 3 by 3 matrices, we can get back to where we were really going, using determinants to take the cross product of two vectors, u and v. And I haven't written out all the details, but I am thinking about the vector u as being u1, u2, u3, and the vector v having components v1, v2, and v3, and then we got this formula. And here I've reminded us how to take the determinant of a 2 by 2, kind of in an odd way though, right? Because, A, B, C, D, instead of doing that, I called it U1, U2, V1, V2. Well, those are just numbers, and that gives me this. But right away, I notice that looks a lot like the K component of this cross product up here. This looks like a determinant. And if I think about it, these kind of look like determinants too. And so I'm thinking that this is a 2 by 2 determinant times something. And this is 2, and so is this. And that reminds me of that way in which we find the determinant of a 3 by 3 by expansion. If I call that top row A, B, C, well, then I had A times a matrix formed by whatever's here and here, plus B, minus B, times whatever matrix is formed by things in these spots, and then plus C. All right, well, thinking about it, if I was trying to get this in the last spot, I'd need to take out where C is, right? And that would give me, well, that little 2 by 2 matrix. U1, U2 on the top row, and V1, V2 on the bottom row. And then I said, well, I don't want to multiply it by some number C. I want to multiply it by the vector K. So instead of having a number in that top row, what we're going to do is we're going to put the vector K up there. And, I should write it here. Most of the time when I write this formula down, I reverse the order of multiplication because order in multiplication doesn't matter. All right, well, let's just see what happens if we rethink this with an I and a J, right? That standard basis. Well, this would become an I. And then this little matrix should be what happens when I take out the first row and the first column. U2, U3, V2, V3. And if we check it, U2 times V3, and then U3 times V2, and the subtraction's in the right order, and this formula works for the first component. We know it already works for this one. So all we have to do is check this last one where this B should be replaced by vector J. All right, U1, U3, and V1, V3. All right, well, I have U1, V3 minus U3, V1. This determinant calculation gives me the cross product of two vectors. So when I'm asked to evaluate a cross product of vectors u and v, what I like to think of as the definition is that u cross v is equal to this determinant. And this makes a very efficient calculation formula because I know how to expand across the top row and then evaluate those little 2 by 2 determinants. And the way I typically write this down expanded is this, with the multiplication of the matrix and the unit vector reversed, because that's how I typically write down my vector. All right, that's how I like to define the cross product. One really cool thing, if I have vectors u and v, the cross product follows a right-hand rule. So if you take the cross product of v and u, that would have to be the same vector, but pointing in the opposite direction. So better said, same length, but going opposite. Well, it's a property of determinants that if you swap two rows, the signs change. All of the signs would change. And so you literally get that U cross V is the opposite of V cross U. Okay, so let's actually evaluate a cross product using this formula. Find U cross V. For vectors, U is the vector 1, 2, 3, and V is the vector 3, 0, 1. To me, U cross V is always this determinant. All right, just writing out my little minor matrices. Now all I have to do is take little 2 by 2 determinants. I get 2 i's. Let's see, 1 minus 9. That'd be a minus 8, but minus a minus 8, plus 8j. 1 times 0, minus 6, minus 6k's. This is the vector that is U cross V. That vector is orthogonal to both of these and has a length that's equal to the area of the parallelogram that they span. So, a couple of important notes about the cross product. If you take the dot product of U with the cross product of U and V, you have to get 0. Those are perpendicular vectors. Same thing with vector V and then U cross V. They're mutually orthogonal. All right, so you can actually show this by writing out U and V in symbols and then writing out what the cross product would be in symbols here and actually doing the dot product, distributing everything out and making sure that everything cancels out. And that's a pretty good exercise for you to go through. It's 2. I said this one a minute ago. U cross V and V cross U are opposites. They have opposite signs. So if you know U cross V, you can automatically write down V cross U just by swapping all the signs out. The magnitude of U cross V is the magnitude of U times the magnitude of V times sine of the angle in between. An explanation of this fact is actually linked in a handout below this video. And the fourth thing I want to make note of here at the end of this video is the cross product follows a right-hand rule from U to V, which means order matters. U cross V is not equal to V cross U, kind of what we have written right here. All right, so I think you should try to show this one. This one can be thought of as a property of matrices, also a property of that right-handed rule. This one, explanation of this is linked in a handout. And if you want an explanation of this one's in your textbook actually, using properties of the cross product.